Unit 4, Objective 2, multiplying and dividing rational expressions. And remember, rational expressions is nothing more than another term for saying ugly fractions. Now, in this objective and in pretty much all the other objectives in this unit, your factoring skills are going to play a really major role in how either easy or how difficult you find these concepts to be. Example number 1. I'm multiplying two ugly fractions, but they all happen to be monomial terms, so it's just a matter of reducing what I can, and then whatever I'm left with, that's what I'm left with. I can take that 24 and that 2, and I can reduce across if I want, or I could take the 24 and the 8 and reduce up and down if I want. Why don't we say, let's go across first. The 2 and the 24 would make a 1 right there, and the 24 would turn into a 12. Now I can go up and down with that 12 and 8. They're both divisible by 4, so I can reduce by a factor by 4, and that would make the 8 a 2 and the 12 a 3. And I think that's about all I can do as far as the numbers are concerned. Let's start looking at the variables. I've got a c to the 5th divided by c squared. When you divide exponential terms that have the same base, you just subtract the exponents. So if there's 5 up here and there's 2 down here, when these 2 reduce with 2 of those up there, the c squared is going to go away, and the c to the 5th is going to get reduced by 2, so it's going to end up being c to the 3rd. Now, looking at anything else I've got this d over that d, so I can reduce those. And I think that's about it. And now that I have finished all the reducing I possibly can, let's see what I'm left up with in this problem. I've got that 3 multiplied by that 9, which is 27. Now I've got this c cubed multiplied by that c, so that would be c to the 4th. And I think that takes care of the numerator. And for my denominator, the only thing I'm left with down here is that d cubed. So that's the answer to that problem. That is that fraction reduced or simplified. Now notice there was no factoring involved in that problem because all of these were monomial terms. Let's jump down to example number 2. Every single one of these parts of these fractions need to get reduced. Factored, and then we can reduce. So let's just take them one at a time. This top, the numerator of the first fraction, can be reduced through the greatest common factor method. They both have 6x, so I'm going to factor out of 6x, and I'm going to be left with x plus, now 6x divided by 6x doesn't just go away and become nothing, it becomes 1. Now the denominator of the first fraction, I've got a trinomial, but there's a leading coefficient of 2. So we're going to have to do a guess and check. So 2x squared as my first term means one of these is going to be 2x and the other one's going to be x. Now for the second term, I've got minus 15, which can either be the pair of 15 and 1 or 3 and 5. Let's go with the 3 and 5 first, but I've got to get a negative 1 right here. So the only way that's going to happen is if I put a minus 3 right there and a plus 5 right there. Now if you do your FOIL, you're going to see that 2x plus 5 multiplied by x minus 3 does give you 2x squared minus x minus 15. Now, moving on to the second fraction. X squared plus 7x minus 30. Factors of negative 30 that add up to positive 7 are x plus 10 and x minus 3. And then down here, the denominator of the second fraction, this is another GCF. They both have 3x, so I'm going to factor out a 3x. And I'm going to get left with, if I factor a 3x out of 3x squared, I'm just going to get an x. And if I factor a 3x out of a 3x, again, it doesn't just go away. Okay, now, what do we have that cancels? I've got an x minus 3 and an x minus 3 that reduce each other. I have this 3x and that 6x. Okay, these x's can reduce each other. That 3 and that 6 can reduce to a 1 and a 2. And I believe that's about all I've got left. I've got 2 times x plus 1 times x plus 10 over 2x plus 5 times x minus 1. And since that's the only thing that's remaining after everything else reduces away, that's your final answer. I've turned the dial up a few notches on example number 3. Notice, first of all, this isn't a multiplication problem. This is a division problem. So we need to remember our rules for dividing with fractions. It's pretty easy. You learned them in elementary school. The division sign changes to a multiplication sign. And the second fraction simply flips. So that takes care of that. The division problem is no longer a division problem. It's a multiplication problem. Now, the next thing you need is every single part of this problem needs to be factored. So we're going to practice our factoring methods. The numerator of the first fraction is a 4-term polynomial with nothing in common. And so therefore, we're going to factor by grouping. The first two appear to have an a in common, so we're going to factor out an a. And if you factor out an a, you're left with 2c plus 1. A over a is 1. They don't just cancel and go away. They reduce to become the number 1. So that would be 2c plus 1. Now, the second two terms, they have a negative 5 in common. So we're going to factor out a negative 5. And negative 10c divided by negative 5 would be positive 2c. And negative 5 divided by negative 5 is positive 1. So again, it's doing exactly what it's supposed to be doing when it's factored by grouping. We have a 2c plus 1 as the common factor. And we have a minus 5 as the other factor. Now, that took care of the numerator of the first term. Let's move on to the numerator of the second fraction. C squared plus 11c plus 28. This one's a little bit easier. It's a regular trinomial with a leading coefficient of 1. The factors of 28 that have a sum of 11 are 7 and 4, which means my two factors are c plus 7 and c plus 4. Now, let's move on to the denominator of the first fraction, c squared plus 3c minus 4. That's another regular trinomial just like the last one. All I'm looking for are the factors of -4 that add up to +3. So you can see I've already got it factored. It's c plus 4, c minus 3. And now moving on to the denominator of the second fraction, 7a minus 35. This is going to be a greatest common factor. All I have to do is factor out the 7 that's common to both terms. And I've got 7 multiplied by a minus 5. So now, at this point, I have factored all of the parts of this problem. Now, let's take a look at what everything is in its factored form. So we're going to go back, take that multiplication problem. After we turned it from division to multiplication, this is what it looked like unfactored. Let's write it in its factored form. The numerator was 2c plus 1 times a minus 5. The denominator of the first fraction was c plus 4, c minus 1. The numerator of the second fraction was c plus 7 times c plus 4. The denominator of the second fraction was simply 7 multiplied by a minus 5. So here's the problem in its fully factored form. We start reducing what we can, this a minus 5 and that a minus 5, this c plus 4 with that c plus 4, and that's about what we've got left. Everything we've got left is going to be the answer. 2c plus 1 times c plus 7 over 7 times c minus 1. Example number 4 looks bad, but to be honest with you, I think it's actually easier than example number 3. It's presented as a complex fraction. A complex fraction is just fractions within fractions. Notice the numerator has a fraction in it and the denominator has a fraction in it. But really, all you have to do is think of this main fraction bar right here, the one in the middle, as a division sign. So I'm going to turn this from a vertical fraction problem to a horizontal division problem simply by doing that. I've got 49 minus x squared over x squared plus 2x minus 3 divided by, and then the denominator, x squared plus 3x minus 70 over 5x plus 15. And now that you've taken it from this form to this form, now we know what to do with it. The way you divide fractions is, you change the division sign to multiplication, and you flip the second fraction, and so really that's all I did. Now, I have to factor every part of this, and then let's see where that takes us. 49 minus x squared is a difference of perfect squares, and that becomes 7 plus x times 7 minus x. X squared plus 2x minus 3. A regular trinomial, factors of -3 that add up to +2 are x plus 3 and x minus 1. Multiplied by the numerator up here, greatest common factor. I'm going to factor out a 5, and I'm going to be left with x plus 3. The denominator down here, back to a regular trinomial, factors of -70 that add up to +3. and that would be a combination of 10 and 7, x plus 10, and x minus 7. So that's the problem in its fully factored form. Now we just need to start reducing what we can. I see this x plus 3 can reduce with that x plus 3. Now, I do see something, it's not perfectly the same. In fact, they're exact opposites. This 7 minus x and that x minus 7. They are exact opposites, and when they reduce, they don't just make 1, they actually make negative 1. And I think that's the best I can do, so now I'm just going to rewrite whatever's left in the problem. I've got 7 plus x on the numerator. I've got 5 on the numerator, but I also have a negative 1, so I'm just going to do this really easily and make that 5 a negative 5. That's the easiest way of dealing with that negative 1 over x plus 10 times x minus 1. And there's your answer to example number 4.